Welcome back to Statistics Made Easy, your go-to channel for breaking down complex statistical concepts into easy to understand bites. Today we're diving into a couple of terms that might sound intimidating but are super helpful in data analysis: robust and clustered standard errors. Let's first talk about robust standard errors. Imagine you're analyzing data to see how temperature affects ice cream sales. You'd expect that as temperature goes up, more people buy ice cream, right? But what if your data points are all over the place? Maybe there was a festival one day that spiked sales, or a sudden rainstorm that dropped sales unexpectedly. It could also be that there are simply more differences in ice cream consumption at medium temperatures, when some people still find it too cold for ice and others find it just right. These irregularities are called homoscedasticity, a fancy word meaning the spread of your data points isn't consistent. Normally, we assume that the spread or noise is even across all data points. But when it's not, robust standard errors come to the rescue. Robust standard errors adjust for this inconsistency, giving you more reliable analysis and estimates even when your data is a bit messy. Similarly, we can also use clustered standard errors. Imagine you're looking at ice cream sales across multiple locations. It's likely that sales in the same location are more similar to each other than to sales in different locations. This is because of factors like local temperature variations, events, and even local habits. In our case, there is very little ice cream consumption for lower temperatures in the park, which could be explained by the fact that it is generally shadier in the park and therefore the perceived temperature is lower than in the city center. These groups are called clusters. When analyzing this type of data, we need to account for the fact that data points within the same cluster, or here location, are more alike. Clustered standard errors do just that. They adjust for the similarities within clusters. So, what's the difference? Robust standard errors deal with irregularities and inconsistencies in the data spread overall, while clustered standard errors handle data grouped into clusters, accounting for within cluster correlations and inconsistencies. To sum it up, using the right type of standard error ensures your analysis is more accurate and trustworthy. Whether you're studying how temperature affects ice cream sales or any other relationship, robust and clustered standard errors help you get reliable results. Now let's see how we can implement robust and clustered standard errors in Stata. I open the multivariate statistics do file, which I already know from my previous sessions on statistics and regressions, and load the ice cream data into Stata's memory. That's the data set we created during the data preparation tutorial. I scroll down a little to model 2, which is my baseline regression. In this model, ice cream is my dependent variable and temperature, child, income, and location are my independent and control variables. To check for homoscedasticity, that is whether my data is subject to noisy or not evenly distributed residuals, I can use the following methods. First is visual inspections. Plot the residuals versus the fitted values. If the spread of the residuals increases or decreases with the fitted values, it indicates homoscedasticity. Please check my videos on the descriptive statistics and using Python in Stata for practical examples of these plots. In addition, we can perform a Breusch-Pagan test, a formal statistical test that can be performed in Stata using the estat_hat_test command. And that's what we're going to do now. This tests the null hypothesis that we have constant variance, another term for homoscedasticity, the opposite of heteroscedasticity. In simple terms, we have to reject this null hypothesis given the low p-value here of close to 0, that we have homoscedasticity and equal variance or constant variance. In this case, we are better off using robust standard errors in our regression model. Alternatively, we can also use the white test, another statistical test that can be performed using Stata's emtest post-estimation command. Both these tests can only be run after the regression because they reference the previous regression. In this case, we have a very similar null hypothesis, namely that we have homoscedasticity. Again, given the low p-value here, very close to 0, we have to reject that null hypothesis. We violate that homoscedasticity assumption, and according to the test statistics, we should use robust standard errors. We can implement robust standard errors in Stata by adding the robust option to the regression. As you know, options are always indicated by a comma, so I add a comma after my variables in the regression and then add robust to that regression command. If I run this adjusted regression command, I get now the adjusted and robust standard errors in my output. I scroll quickly upwards to see the original estimates of my baseline command and take a look at the income variable, which in this case is statistically insignificant with a relatively high p-value of 0.155. If I scroll further down, I see the adjusted robust standard errors in the second column and also correspondingly the p-value, which is now much lower, turning this income variable statistically significant. So depending on how you estimate your standard errors, the results can change quite a bit. Unfortunately, there is no formal statistical test to determine the exact level at which to cluster your data. The decision to cluster is mostly based on theoretical arguments, but there is no real test that you can rely on similar to the robust standard errors. But you can use, for example, a scatter plot in which you highlight different groups in different colors to see if some groups within your data differ in their variance structure. In our case, observations within the same location may be more similar. To account for this clustering, you can use the cluster option and specify the cluster variable in parentheses. In my case, this would be the location variable. So I'm going to add the comma again, followed by cluster and in parentheses, the location variable. Notice I need to omit the I dot in front of this variable because factor variables are not allowed when using the cluster option. This command adjusts now for the within cluster similarities, giving us the correct standard errors for this analysis. In this case, you can see that the p-values of the child and income variables are slightly higher compared to our regression with robust standard errors. Of course, you can also combine robust and clustered standard errors in Stata to account for heteroscedasticity and any clusters. I can simply add robust to my regression command, rerun this estimation, and then I get the adjusted standard errors. Perhaps one nerdy remark on controlling for the location effects and clustering standard errors at the location level. Yes, you can include location dummies as controls and still cluster standard errors at the location level. This approach is not redundant. It serves different purposes. Location dummies control for location-specific effects. Including location dummies helps adjust for systematic differences in locations. Clustered standard errors address potential correlation within each location in the standard errors. In other words, clustering standard errors accounts for any remaining correlation within these location clusters. So what's the punchline? It is generally advisable to use robust standard errors when there is a risk of heteroscedasticity. Use clustered standard errors when there is potential for intra-cluster correlation in the data. However, always using these methods without considering the specific context of your data can lead to inefficient estimates. So first, plot your data, run the test statistics we discussed, and make your selection based on that inspection. That's it. With just a few adjustments, you can ensure that your regression analysis is accurate and robust, whether you're dealing with heteroscedasticity or clustered data.